Okay, continuing from yesterday, thank you. So the thermal energy is calculated with this awesome equation, and if this is a delta, not an A, but it kind of looks like MCAT, and that's how I remembered it. The mass of the material times its specific heat value times the change in temperature that it experienced will give you the amount of heat energy that you had to put into that. So you take a piece of something, you stick it in fire, and it absorbs thermal energy, and its temperature will change based on its value for the specific heat. So the higher the specific heat value, the more energy it takes to raise its temperature. And this equation will be used by you many times here, and many, many, many times in physics. We spend a long time on that equation. So it will become your friend by the time you're done with school. Moving on here, this is just an example. If you were to add the same amount of, if you wanted to raise a kilogram of gold bought from 20 degrees to 90 degrees, and also you wanted to raise a kilogram of water from 20 degrees to 90 degrees, it takes about 30 times the thermal energy to raise a kilogram of water the same amount of temperature degrees as it does a kilogram of gold, because gold has such a low specific heat and water has such a high specific heat. So water absorbs more heat before it starts to change its temperature. Okay. Same reason why if you're cooking and you have a wooden spoon in a pot of soup that you're stirring, and you leave the wooden spoon in the soup and then come back to it later, you can grab the wooden spoon and keep stirring, and the wooden spoon doesn't burn your hand. But if you did that with a metal spoon, if you're stirring with the metal spoon in the soup, and you leave the metal spoon in the soup, and you go walk away and you come back later and just grab the metal spoon, it will be stinking hot. That's because wood has a much higher specific heat, and so it can absorb the thermal energy from the soup, and its temperature doesn't change very much. Metal, low specific heat, it absorbs the thermal energy from the soup, and it gets hot. That's why wooden spoons are good for soup. And then just so you've seen some of the ways that we express this, the value of C for specific heat is in units of joules per kilogram degree Kelvin. And some of the numbers here, the larger the number, again, the more thermal energy it absorbs before its temperature changes. So something with a relatively small number like diamond changes temperature very quickly. 500 joules of energy, which is not that much energy, will raise a kilogram of diamond. Boy, don't you wish you had a 2.5 pound diamond. A 1 kilogram block of diamond, 1 degree Celsius or Kelvin. So it doesn't take much thermal energy for that. Compare that to helium, which has a specific heat of 5,193. It takes 5,000 joules to raise a kilogram of helium, 1 degree. Okay, so a lot more energy there, and water is obviously a fairly large number as well. When you compare it to metals, have a fairly low number. Okay, let's do an example here. If 0.58 kilojoules, so that's 580 joules, if you were to write it out in normal numbers, of heat energy are added to 23 grams of ethanol at 13 degrees Celsius, what will the final temperature be? So it starts at 13. I'm going to calculate the change in temperature based on the value for C and the mass of the ethanol that I'm using here. I've got a table of specific heat values. This is given to us in kilograms and degree Kelvin. I have degree Celsius. The width of a degree Celsius and the width of a degree Kelvin is the same. I don't have to convert. And so joules, kilogram, Kelvin. I have kilojoules. I need to get to joules. And I have grams. I need to get to kilograms. And I have Celsius, but I can leave it. So let's do this math. Ethanol is a specific heat of 2410 joules per kilogram. We have 0.58 kilojoules and 23 grams, but the constant is not given in those units. We need to do a little conversion. So 0.58 kilojoules is 580 joules. 23 grams is 0.023 kilograms. Okay. Now I can use my formula, and I've got my table out of the way. Q equals MC SP times delta T. Oh, sorry, it bled over. Somehow the font didn't like that size. Put everything in. Here's my value for C. Here's my value for Q. Here's my value for M. And then I'm just calculating delta T. Multiply it all across and divide to get delta T by itself. And I have a change in temperature of 10.46365 degrees Celsius. Okay? I need to correct for significant figures, so basically 10 degrees Celsius. If it started at 13, then the final temperature will be 23 degrees Celsius. So if I take that quantity of ethanol already at 13 degrees Celsius, add that quantity of thermal energy to it, then I take its temperature again, it will be at 23 degrees Celsius. Okay, do you guys see how this math works? Questions? Okay. Enthalpy of reactions. Balanced equations that show the amount of energy absorbed or released are called thermonuclear equations. Sounds like we're going to blow up a foreign country, but we're actually just letting chemical reactions happen in our lab. It's not as dramatic as it sounds. Thermonuclear equations will demonstrate the change in enthalpy, or the change in thermal energy, right? And we use H for this. So the total change in enthalpy is equal to the change in enthalpy of the products minus the enthalpy of the reactants. So the energy available in the products that you start with, and then you subtract the energy, the thermal energy of the reactants when you're done. If you get a negative value for delta H, then it's an exothermic reaction. And there was more energy available in the reactants than in the products. It gave off energy. So that's exothermic. Positive values for H are endothermic. So that means that you had to add energy to get this thing to happen. Right? So here is, let me pause for a moment if you're still writing. Oh, I thought I had an example there. I guess I have an example later. Most compounds have an accepted value for what's called the enthalpy of formation. And that is how much energy does it take to make this thing? Or you could look at it as how much energy does this thing have because it is itself. So the enthalpy of formation, the amount of heat energy or thermal energy present in that substance. Now we have to assume that it's at a particular temperature because thermal energy will change that. But when we'll say when it is formed, when we make it, what kind of thermal energy does it either absorb or give off? And there will be a value for it. Okay. So for some substance, like pick something, sugar, there will be an enthalpy of formation value for sugar. And what that means is when you take carbon and hydrogen and oxygen from their natural native states and you arrange them to become sugar instead of carbon, hydrogen, and oxygen, what kind of heat is either absorbed or given off? Okay? Most values are negative because most things are, the formation of most things is exothermic. It gives off heat energy as it is formed. There's a molecule of something is more stable than the free elements floating around in the universe. So most things have a negative value for the enthalpy of formation, and it's always composed to the energy of the component elements. Like I said, sugar as a molecule versus carbon, hydrogen, and oxygen as pure elements. The energy is given off when you make sugar, okay? And so it's a negative value. Most things have a negative value. There are some things that have a positive value, but it's definitely the exception. There's a table in your book that gives you the enthalpy of formations for lots and lots of things, and you will become very familiar with that table this chapter. You will get to do a lot of calculations of enthalpy of formation or enthalpy of reactions, where you need to look up the values. Okay, so you'll get to know that. And in our labs that we'll do starting tomorrow, you will get to use this as well. Okay, so you'll be looking at how much thermal energy is resident inside a particular compound. And so to calculate the delta H for products and the delta H for reactants, what we have to do is look at the energy of formation, the enthalpy of formation for all the products, and then for all the reactants, and then subtract. So the summation of the values for the enthalpy of all the products minus the summation for the enthalpy of all the reactants. And then when we do this, we'll get a calculation for delta H, and we'll be able to say that this reaction is exothermic or this reaction is endothermic based on the values that we find. Okay, so now we do have some examples here. I'll give you a moment to finish writing. Okay, I had to make ammonium chloride for a lab, and I used hydrochloric acid and ammonia to make the ammonium chloride. So was the reaction that I did exothermic or endothermic? Well, you could do the lab, you could measure the temperature, mix it together, measure the temperature, and you can experimentally verify that it's exothermic or endothermic. But you can also calculate it and see if it's going to be exothermic or endothermic. So my reaction was ammonia plus hydrochloric acid gives me ammonium chloride. And so I need the enthalpy of formation values for all those things. And you can look it up in a table. And here's a table. This is actually the table that's in your book, okay? And you will get to become friends with it. So when I look up the table, the values here, here is hydrochloric acid at negative 92.31. Here is ammonia at negative 45.9, and here's ammonium chloride at negative 314.4. So you would look up the things that you need, okay? And once you've done that, you can take those values back. So HCl, NH3, NH4Cl. And you use them in this equation, right? So the summation of the products minus the summation of the reactants. Summation of my products, negative 314.4, that's easy. I made ammonium chloride, and it's the only thing in the products. So that's easy. Minus the summation of my reactants. My reactants was negative 92.31 and negative 45.9. Add them together, I get negative 138.21. If I subtract, now watch your signs. This is 7th grade algebra, pre-algebra stuff. But make sure that you just watch your signs. You're subtracting a negative, so that actually turns into an addition statement. So negative 314.4 plus 138.21 gives you negative 176.19 kilojoules. So my value for delta H is a negative number, which means it's exothermic. Okay, it released 176.19 kilojoules of energy when I did this. Watch your significant digits. Here I have 4 and 3 and 4. I should have only recorded this as 3 significant digits. Sorry about that. That's a typo in the exam or in the lecture. Should have been 176 even kilojoules. Okay. So that's the kind of stuff that we're going to be doing in this chapter, and it gets deeper. We look at more forms of energy reactions later, but cell phones time. But this is good enough for now. So you'll be looking up values in tables and doing some addition and some subtraction. It's not hard math. It's just weeding through these large tables to find the numbers. Okay? That is it.